and when it's gonna start. Please, now the floor is yours.
Hello everyone, my name is KOUSHIKEY CHHAPARIYA. Bonjour. I'm a PhD student, and today I'll be presenting about hyperspectral image analysis with deep learning. So before getting into the presentation, a very brief introduction about me. As I mentioned, I'm a PhD student and I'm doing my PhD from India, Indian Institute of Technology, Bombay. And I'm working with a convolution neural network based model for detecting selective features on hyperspectral images. Basically, I'm working with satellite image processing. And I have been awarded with Raman Charpak Doctoral Fellowship, on which I have come over here as to complete a part of my objective for 6 months. So what is hyperspectral? Like, I will present my presentation in 2 sections. One is, I told you, hyperspectral image analysis, then what is that? And another section is, what is deep learning and how I'm integrating deep learning and convolution neural network with satellite data. So first, unlike normal images, which I meant the images which we click from your phone or a camera, we have 3 bands, particularly 3 bands, like red, green, and blue. But with hyperspectrals, we have thousands of bands. So that's make a difference with the hyperspectral, where we have a continuous, spectrum, or we can say it, when we talk about wavelength, there are so many different bands that it occurs as a continuous instead of for multispectral, which appears as a discrete bands. Again, this is a challenge because it's a very large number of bands, so it's difficult to process and to analyze them. Again, why hyperspectral? Like, why cannot we go with multispectral, and why we need this 100 bands and 1000 bands? Firstly, when we talk about satellite images, the data captured is an overhead data. So it's completely different perspective and the orientation is different. So we need to identify what kind of object we are detecting. And we cannot do with normal multispectral images. Why I'm telling you? Because, for example, if I have to tell you to distinguish between a normal plane or a fake plane, you cannot do it if I'll just keep you and I'll tell you to just observe it and tell you if they look exactly same in color, texture, shape, etc. That is what is spatial resolution when we talk about satellite data. There's something called spectral resolution. Spectral resolution is knowing the property of the material. Like a normal plane or a real plane will have a different curve because the light reflected from that plane will be totally different comparative to the fake planes. And that is how we distinguish with the satellite data. And this is, I'm talking about, like, when I talk about a plane, your image will be like 2 planes. No, but I'm talking about a very wide area. It could be a very wide area when we talk about satellite images. And that is why we need deep learning to automate this process. So there are a few terminologies I wanted to get familiar with. First is semantic segmentation. When we need to we need to segment or identify uncountable objects like road, sky, etc., we go for semantic segmentation. For instance, we go for objects like car, people, which can be countable. And we can say how many cars are there if we have a picture and we need to detect that. And panoptic segmentations are a combination of semantic and instance, which we can do both uncountable and countable objects. So what was my problem statement for the work I was doing? So I told you, like, with hyperspectral data, we have a large number of spectral bands. That is, we have very good spectral resolution, which means we can identify an object's property based on the wavelength we get. But we don't have spatial resolution, which is the texture or shape of the object. With my objective with my research is to incorporate that spatial resolution along with the spectral resolution of the hyperspectral data, and that I'm planning to do with deep learning methods. So there are 3 dimensions of convolution neural network: 1D, 2D, and 3D. So with my research, I have objectified with 3D convolution neural network. And why I went with 3D? Because 1D convolution neural network takes care of spectral information. So if you'll see this image, we have, when I meant spectral information, it's in one direction. It means the number of bands we have. So it's just in one direction, and the equations where you can see Z plus L, Z represents the number of bands. But when we talk about two-dimensional convolution neural network, we have height and width, which is like the spatial information in X and Y direction. So that is what X and Y plus H plus W, the height and width of the images tells about. That is why we go for 3D convolution neural network, because my objective is to have both spectral and spatial information. So I have X and Y, which is the spatial information, and Z, which is the number of spectral band. But the question is why we cannot go with, we can take 1D and 2D and combine them and then do the research. Why we have to go for 3D convolution neural network? Because 3D convolution neural network it takes a lot of time to process. It's more complicated. The idea was, because there was two ideas behind it. First was, if we combine 1D and 2D CNN, still there was some information loss, and that we observed. While with 3D CNN, our hyperspectral can be represented in a 3D cube. And with 3D CNN, it was a proper, there was a proper channelization where we can use 3D cube and 3D convolution neural network without reducing the data dimensionality. So this is one of the methodology which I use, which is multi-level 3D CNN. The input image which you can see, is a satellite data, and I have taken a patch of that image, the input image, and I've considered 4 convolution layers, in which 2 convolution layers I have kept like 3D convolution network as a 3x3 kernels, while the two convolution blocks I have considered is as a level. In that level, I have considered different kernel sizes. So if we talk about level 2, in the conv 2.1, I have taken a kernel size of 3x3, while conv 2.2, I have taken a kernel size of 7x7, and 2.3, I have taken a kernel size of 11x11. So the idea was, when in satellite images, the size of the features differ with, the ratio of the size differs very vastly, because again, it's an overhead, a wide area, and blah, blah, blah. So we wanted to extract the features of all small as well as the large features. So that is why we varied our kernel size, so that we can detect all these different kinds of features. Apart from that, I have used the ReLU, which is an activation function. So that main purpose of activation function is to increase the method and the firing process of the deep learning method. And then I have used a max pool, dropout, and fully connected layer. So max pool is to take out only the main information that is required, and dropout, because since we have a lot of network, all these networks are not required. So all these connections are not required, which can make my model more complicated. So this was the layer-wise parameter which I have shown for the method which I recently showed for multi-level 3D CNN. So I have, as I told you, for the 2 block, I have used different size of kernel, and the padding means when we take our image at the boundary, there's sometimes that boundary images get crops off. To take the whole image, we do padding. Padding is like adding zeros or 1 at the corner or the boundary of the image. So this was the experimental results. So just observe about the overall accuracy in kappa coefficient. The terminologies, which is IP, PU, KSC, and BW, is different hyperspectral data set, which I'll show you. IP stands for Indian Pines, PU for PVA University, KSC for Kennedy Space Center, and BW for Botswana. So these are the names of the data set that I have used, different hyperspectral satellite data set. So that is none of concern, but the patch size is concerned. Like what I did was, the hyperspectral image I have taken is a very large data set. So I cannot take the whole data set into one section. So I take a different patch size of the images. And when I consider different patch size of the images, I saw, like, when I'm taking the patch size 7, I'm getting the maximum overall accuracy and kappa coefficient. So this is the Indian pines, the data set which I'm talking about. The first A is the RGB image, which is red, green, and blue, just the 3 bands image to show the data. And then was the labeled ground truth, which we were having from the training data, and then the classification output with patch size 7. Similarly, this is for the Kennedy Space Center. You can see the satellite data. They have a lot of information like bridges, rivers, land areas, land covers. This is the Pavia University. And again, this is Botswana University dataset. So now this was the work I did when I was in India, and coming over to France, I'm working on a data set called TIGA, which is a novel data set for multitask learning. So what is multitask? Like till now, the work which we were doing were just the classification for a, when we talk about classification, we are categorizing any features like, okay, this is my trees, or this is my land, or this is my water. But when we talk about multitask learning, there are different kinds of data in that, which can be categorical, which are categorical and continuous. So categorical as like they have classes, which we can identify by saying, okay, this belongs to this class, while continuous is the parameters with the features that can extend at a certain level. So if you see, like that is why categorical, the number of classes is like 4, 2, and 3, which is like the number of classes that can be identified. While for continuous, we have ranges, the range which it can expand. So for we did some data pre-processing to identify that how many classes we have in our data. So for the fertility class, we were having 4 data with different percentages, which means like the class 3rd have the highest percentage, while for soil class, the class 1 have the highest percentage. So that one thing which we can observe from this is that we have data imbalance. So we need to balance our data to do the prediction. Otherwise, if we have like if we not take care of the unbalanced data, then the prediction at the end of the prediction, the results which will be more for the class 3 or the class 1, or similarly for the class 1 for the main tree species. Similarly, this is for the continuous data. So first thing which we did was splitting it into training and test mass. So we make sure that all the training and test mass do not coincide with each other. And then I took a section of the data and do the classification using the multi-level 3D CNN model which I showed. And you can see on the middle part, that is the classified output for the fertility class. Like we were having 3 classes, fertility, soil, and mean tree height. So the middle one is the classified output for the fertility class. This is for the soil classes, and this is for the tree species. So this multitasking, the categorical classification is there, and this is the overall accuracy in kappa along with the accuracy graph which we get. And this is with the continuous data. So for the continuous data, we did root mean square error and relative root mean square error and relative bias error to see how my error is fluctuating when we are doing the multitasking for the classes. So the next step would be to do the multitasking model, where we are trying to, like right now when I was doing the multitasking, I was firstly doing the classification, the categorical classification, and then the continuous classification. The next step would be to optimize it and to channelize it into one proper channel, where when there is a categorical, or either it is a classification or a regression that can be done simultaneously. Secondly, what we can observe is the losses for the regression are slightly high comparative to the classification part. That could be because when we are trying to channelize both at the same time, we need a different kind of losses, like cross entropy loss or the mean absolute error loss or RMSE loss. So we need to channelize which loss can be at a section where both can be taken care of when we are taking classification as well as regression. And along with that, since it's a satellite data, which is a very large data set, so I need to do the pixel level prediction as well to see what are the chances of getting, pixel level misclassification when we are talking about regression and classification. Merci beaucoup.
Thank you very much. So if there are any questions, maybe you can start with that. Yeah.
So your current model is doing multitask, or
Yes.
is it a future improvement?
So the multi-level 3D CNN, which I showed,
Yes.
was not capable of doing multitask learning because we have to do in a sections, which was not our purpose. So we are developing a new model for deep learning, which I have not incorporated in it right now. But yes, the model, which again, the model is based on convolution neural network, of course. And that what we are trying to focus is to take both regression and classification simultaneously.
Any other questions?
It's me again. Like for your results, for example, is it like steady results? Like if you train it again, do you get like the same level?
No, of course no. So
Yes.
at every seeds, we're getting a fluctuation of point something. So that is why when we are for this result, for the Tiger data set, when we are trying to show our results, we will keep a gap, like we can show the maximum and the minimum, and we can show for how many number of seeds we're getting that difference.
Very nice.
Yeah, so sorry, I wasn't quite listening full 100%, so I'm just asking now. Can you go back to your results, the last ones?
Do you mean this?
Yeah, this, for example. So I'm not sure if I understood, but do you use like some pixel for training and some other for testing?
Yeah, yes. So if you see here, I made sure that the training and testing do not overlap, so I can have a like unbiased result.
And have you tried your trained model on something totally different? Let's say you have a few images, you train on a few, like you did, but also test on some image that you never touched before.
Okay, so what you are telling about is something called as transfer learning. So we train on one kind of data.
What I mean is that realistically, if you want to use your model, you won't have the ground truth on the thing that you want to try. So you won't be able to just try it with things that are very close to what you tested. Because when you do this kind of random sampling for training and testing, you introduce kind of like a special correlation between what you train and what you test, which can be problematic when you test on other things. So it is really recommended that you have a data set that you never touch. But maybe you did it in a way, because I'm not sure 100% of your thing, because generally when you do this kind of thing, is like you're actually testing on the data set that's very close to your training sample, because it's the same image.
Yeah, that was the main idea what you're talking about. So that's why when we were splitting our data into testing and training and validation, so we make sure that training and testing do not overlap.
Yeah, but I mean, even though they don't overlap, because they're so close pixel, the way you sample, there will be a correlation.
So what you...
Because I'm referring to a study I saw, which really tried to use this kind of approaches and test the models on other kind of things that are close, but not close to the training sample, and the performance dropped a lot.
Yeah. Actually, what you're telling is a good idea, because I have a different standard hyperspectral data set. Yeah. So I can try this model.
Yeah, you should validate on something that's not especially correlated to your sample. What's usually recommended is actually that you split your things in like big blocks. Not for sample randomly.
Yeah, I get your point. Yes.
Because then realistically, what you would have as results in real life would be way poorer than what you have in your data training phase, because of this special correlation. Because maybe the intuition is that maybe when you sample like that, you learn some special things that are relative to your specific data set that you're training on that will not maybe be available on other kind of similar data sets. So since you don't really understand what's happening in the network, you don't know what it learns. And sometimes you can learn some stuff that are really specific to your zone. Or your, so if you, but I know in remote sensing it's very difficult to have a lot of data sets. So this is what we do generally.
Yeah.
So it's not like a critique, but you will have people that will tell you way more harshly than me.
I of course know. Yes.
That this has its limitation.
Yes. Sure. Yes. That's a good point. I'll make sure to do that. Thank you.
Any other question from the audience? Not up yet. Yeah, go on. Go on.
So for your or this architecture you used, what is your number of parameters convolution network? Your total number of parameters.
Exactly, don't remember because it's in thousands, right? Because that's what that calculates. So I don't remember exactly.
Yeah. Okay.
Yeah.
Is it like 1 million?
No, not that much.
Not that
Because no, not that much.
Okay. And so, what is the average number of epochs?
So I for this the multi-level 3D CNN, the number of epochs I've considered is 150 with a batch size of 32. So that's what I consider.
What is your number of samples?
So I think like for the batch size you're talking about, or
no, for like
the training samples,
the total data sets you use.
The training samples,
Yes,
right?
samples.
So like hyperspectral data, the training levels are very less. So I always keep the training data very less. So it's like around 0.2, like 20% to 30%.
Okay.
So that's what I kept for the training.
But what is like the size?
Size of the
data sets?
Size of the
training data sets?
Like I told you, like I do not consider the whole data set. So I keep a patch size of the data set.
Yes, but how many patch?
Oh, okay. So like it depends. Like if my I will calculate the image size, right? Like if my image size is of 200 cross 200. So I'll consider my patch size accordingly. If it's more than that, like this data set, like the Tiger data sets, it's very large. It's I think it's like if I'm not wrong, then it's 700 or something like this in the size. So I consider a bigger patch size. So I consider a patch size of 21.
Okay. So, yeah, okay. Thanks.
Anyone else, or it's my turn? Right, it's my turn, but for all of you, because I think you get already lots of questions. Who among you would be interested in implementing such a method, where it can be useful to use multi-level CNN, 3D CNN, or multitask learning? And what for? Thank you. Can you just,
for 3D CNN, I'm not currently into it, or maybe for time series, I think. But I don't use any time series of data for now, but it could be implemented. But for multitask learning, yes, this is what I currently use. And I had some trouble like thinking the model could be helped like by using several tasks, but it behaves almost as well as when you use the model separately, not like the two tasks. So this is what I'm interested in. For other people that use multitask learning, is actually helpful for the both tasks.
what about the others? Multitask learning, multi-level CNN. Actually, multi-level CNN is pretty good to get different. You wanted to speak, sorry.
Yes, I'm sorry I arrived too late and I need.
Can you have a recap on the multi-level CNN?
No, we could have a discussion together, and if I can have your presentation.
The meeting has been recorded. So.
Yeah, okay. I think I'm interested to test this approach on a project that will start in September with a new student for 3D cloud representation. So I think I'm interested to test this.
Yeah, sure. Can you maybe just kind of recap of the multi-level thing?
Yes. This model is for remote sensing images, which is called hyperspectral data. So the idea was to identify different sizes of the features in a hyperspectral image. So what we did is, since our hyperspectral images are very huge in dimensionality as well as in the sizes, so we take the patches of it, and there's something called PCA, which is called principal component analysis, which is used for data dimensionality reduction. We do not want to use that, because we saw that if we use that, there is a reduction in data. So we use 3D convolution neural network, since hyperspectral can be represented as 3D cube. So in this, we have taken four convolution layers, in which 2 of them are taken into different levels. So the idea for taking different levels was to have different sizes of the kernel. Different sizes of the kernel, because we want to have features of different sizes and ratios in our images, since it's a hyperspectral data. So if you will look into this, maybe this would be helpful. So for the convolution 1, I have taken a kernel size of 3 × 3, while for convolution 2 and convolution 3, which was the middle part, we have taken 3 levels of kernel sizes 3 × 3, 7, and 11. And then we have convolution 4, which is 3 × 3. So this was the whole architecture which we developed for the convolution 3D. And then we have used methods like max fold, dropout, and fully convolution neural network, and a soft max, since we want to do a classification part.
That was the core of the presentation. Right, so no more for multi-level CNNs? Yeah?
How much time to take for training this network?
Training, if I'm not wrong, I think it was precisely 181 or 86 minutes. I have the computed, sorry, not minutes, or hours.
On GPU?
On GPU, yes. But the GPU which I processed was, I think, not that strong enough. Like I think it was the core was not that strong enough, even the RAM. Otherwise, I believe it would be a good GPU that would take lesser time, because the data set is not that big as the data set I'm working over here. So.
Who else is using continuous images? I mean, continuous in time, continuous in wavelength, continuous in anything? No? No one is using?
So we have Marion from Lab, and for Gamelan, so we already use Multitask. We have classification and regression tasks that we do at the same time. And I think we will apply, at the moment, we apply CNNs on 2 channels. But we have, before getting these 2 channels, we actually have small data cubes, like small videos of like 40 samples. And I think that 3 CNNs could be applied instead of reducing 2 channels.
Kind of the same issue she had with lots of bands. Instead of using PCA, just use 3D convolutions to reduce the number. Yeah.
I'm just afraid of the training time.
That's true.
Yeah.
So that is why I shifted with the patch sizes. That really helped me, because when I split my data into different patches, that reduces the computation time a lot. Yeah. But again, the problem would be to identify which would be the best patch sizes. So you have to do, trial and errors to see for different patch sizes, what accuracy you are getting in the computation time. So.
Wanted to speak? You wanted to speak?
Yes. Can we use like this method for like the time series problem, but like the data is tabular data, not like images. So.
Yeah, like what I believe till the time whatever I have worked is, I believe when we are designing a model, the most important part is to know what our objective is, like what we are targeting. So since when I was designing, I know like I have to work on an image, and my image is a satellite data, and I know what kind of difficulties I'll have with satellite data. So what you're talking about, the tabular data, I think of course it can be done, but you do not need to complicate this, this complicated model. It could be done with a very simpler model. So.
Right. By my side, I'm just running out of questions. So if you have anything else to say, please.
With the application, if you'll ask, like, okay, fine, you're doing all this research. What will be your application? Like, I was expecting actually this question. So application-wise, when we talk about hyperspectral, the most important work that is being done, like if you will see right now all over the world, either ESA, NASA, ISRO, everywhere they are trying to have the hyperspectral data. Firstly, because they are very expensive. Why? Of course, to manage the data, hundreds of bands and all. Secondly, the most important objective of these kind of data is crop monitoring. And that's the basic of our survival. So we can identify, like with the normal images, you can know, okay, these are the crops. But with hyperspectral, you can know what type of crop it is, health of the crop. You can investigate about crop, everything what you want, like either a farmland, either a forest or anything. So that's one of the most important things that can be done with hyperspectral data. Along with that, this has been a very, very good application in military. So I mentioned about fighter planes, right? So there has been a case where there were 2 fighter planes and they look exactly same. I do not remember the name, but with the hyperspectral data itself, they were able to identify, okay, which one is this and how that can be useful or that can be like harmful or in this way. So
I would like to also add the fact that here you're just mentioning hyperspectral to watch the Earth.
Yes.
But you can also do the reverse and watch the space. And when watching the space, you can detect some dust thing. I'm not specialist in the field, right? But some dust clouds or things like that you can't see in the visible bands, but you can see with hyperspectral data.
Yes.
So in the end, it might be useful to everyone to have a look on hyperspectral data in its whole. I'm not sure about everyone specialty, right? But maybe, the lab is astrophysical thing, so maybe it can be useful to have a look on hyperspectral images, just to study the astrophysics of the particles.
I have a question. If I have the image like your house, and I would like to convert in the optic one, it can be or not?
So you want to go from hyperspectral to optical?
Yes.
Okay, so correction. Hyperspectral is also optical, but hyperspectral and multispectral, the difference is the number of bands. Yes. So it's more of like when we know what we want to do, like for example, if you just need to do, it's not like you cannot do classification with multispectral. Of course you can do, and people do, and a lot of work. He works in multispectral, if I'm not wrong, right? So we can do a lot of things with multispectral as well. But we go with hyperspectral when we need to identify objects or features which belong to us, which belong to same category. That's what I meant. Yeah. Like if you want to, just classify between land, forest, and water, you can do with multispectral. It's completely fine with very simple model, nothing complicated over there. But when you want to identify different trees or different tree species, or so then you have to go with hyperspectral. So it's something like this.
Yeah. For your dataset, is the image just independent or like
correlation? You mean?
like every image is in independence of the other image, or like there's a time relationship between the images?
So it depends on the satellite swath. Like for example, if my satellite is capturing this area, and my satellite will suddenly not jump to this area and have a, so if it is capturing just this area, it will move slightly and have, so there will be of course an overlap. And there is actually a rule that you cannot have an image unless there is a 30% of overlap between the images. So that is why when we have our satellite data, we have the very important factors which we deal with is the correlation between different bands. When I talk about bands, it means the images captured at different wavelength. We have electromagnetic spectrum, and with each in electromagnetic spectrum, each spectrum wavelength, we have a single band. And every band have a different features or different application. Like we have water absorption band, we have thermal infrared, like different bands together make an image. So of course there is a correlation, and the one most challenge part for us is to take care of that correlation.
Yes, and so you said that some bands are more significant than
Yes.
others. So you did try with multispectral only in the past?
I have worked with multispectral. When I was working with multispectral, then my objective was different. What my objective was, not to identify different species of trees or forest variables or something like this.
So because my question would be, you have significant improvement using.
Yes. So with multispectral, there's a terminology called land use, land cover classification. So I used to do that.
Yes. No, simple.
Is anyone working with classification thing, segmentation thing, or anything else? No one. Yes, kind of.
I used to, but very simple.
I think that this architecture of multi-level CNN might be very useful for classification or segmentation things, especially because of these capabilities of extracting multiple features. Then, if no one working on it,
Just one about segmentation, you presented something in the beginning.
Yeah, I just introduced some segmentation term.
I didn't understand the last one. There were like 3.
Yeah. So panoptic is okay. So semantic is like if in this image, if this is our image, if we need to identify in semantic, it will tell we have people, we have table, we have roof. That's it. But with instance, it will tell how many number of people are there. That also it can tell you. And panoptic is like combination of both semantic and instance. If not, I tell it. Okay, so semantic is like if I'm doing a semantic segmentation, it will just tell you, okay, there are 3 classes. One is there are some people, there are a table, and there's a roof. That's it. But when we talk about instance can tell you, because people are countable, right? Table, there is no count like that, or the roof, there is no count as such. But people we can count, so it can tell how many people are there or how many chairs are there. And panoptic, when we use panoptic, it's a combination of semantic and instance. So in that, it can tell you.
It's like the both thing at the same time.
Yes. Yeah. Yes, exactly. So that multi-level 3D CNN, it's not like very specific to satellite data. If you have a computer vision images, computer vision means the normal images which we click from our camera or a photo or a high resolution data. You can have that. You can you do the classification or segmentation with that model.
Anyone think that can use these kind of architectures in his work, his or her work?
Thank you. For me, it's well, now I'm on glacier ice thickness resolution, which can be very useful. Like you have some very local variation of ice velocity, but like on a more less spatial frequency, lower spatial frequency also. And I like try to use different patch size as input, and it show like when you lower the patch size, you get sharper prediction, like the spatial resolution increase, but it's less able to modelize the global thickness of it, because like I use it as a sliding window.
Okay, got it, yes.
And when I increase the patch size, right, it makes everything blurry and.
Patch size or the kernel? Because
patch size.
Okay.
Patch size only.
Okay.
So, like using a big patch size, but with
smaller kernel.
Yeah, with my kernel is already very the smaller I can get.
Okay. Okay.
But maybe by increasing the kernel size, can like gather more global image of it, and get a sharper product out of it.
Maybe because the patch size which you're considering comparative to your image, you have to see like patch size and the kernel size, they're somehow correlated, I feel. Because, you know, like if you have a 3x3 kernel and you are taking a 7x7 or 11x11 patch size. So I think I felt like that is giving a better result. But, you know, if you're taking a very large patch size, like a 25 or 32 or 64 something, then you need to increase your kernel as well, like a 5x5 or a 7x7. So that's what I felt like.
Yes, probably. Me, I was like using the same architecture to see the effects of it, because it's not like a physical modeling. So we are searching for like the right dimension of it, which can capture the best way. But I switched now to volcano deformation out of deformation, ground deformation observation. And yes, so there is like local deformation and more like broad, larger deformation, which can like maybe can be used with several level model.
Thank you.
I have a feeling that the model doesn't have the information about the wavelengths, and spontaneously it would look like for me that relevant information to have, and so I'm wondering then why the 3D, why you are using a 3D CNN. You aren't losing that information.
Okay, I get that. Then, if you don't know, I'll just.
You can't.
Yes, under there.
Okay, so I'll go there. So I just want to. I got your question. So.
Maybe there.
Okay, I can do that. Okay, so this is how my like image is. It's a 3D cube. So 3D cube, it means it have a length, width, and number of bands, which is making its height. Like, you know, so it have X, Y, and Z. So that is my hyperspectral data. Similarly, when I talk about 3D convolution neural network, so in 3D convolution neural network, we have X, Y, and Z. So with this X, I can take my H, which is the height of the image. With Y, we can take the width of the image. And with Z, I can take the bands of the image. So that is why I take 3D convolution with 3D CNN. Because I really, if I would be just taking 2D. So I have X and Y. Then I can just have H and W. So I cannot take my whole band. I cannot take this Z part.
Yeah, but here you have several images.
Yes.
And you have V, then times you have V images.
Yes.
So you only have pixel information, so it is related to other bands, other wavelengths, other images. And with 3D CNN, you will have the how an image is related to the image of the wavelengths that are close to it.
Actually, I didn't get you. Can you let me know?
It's just that I think the idea is just why you have only a local overview of your 3D tubes because of 3D convolutions, because you are taking only bands that are close together, but not the whole bands when you're calculating your convolutions. So why is this local approach more relevant than the global approach over all bands?
Okay.
And what I was saying is that by having the absolute wavelengths information, the value of the wavelengths, you could have an information about a global, global information about this image.
Okay.
Related to all the other image.
If I'm not wrong, that's what I understood. So there's something when I was mentioning about PCA. So you were telling about the local and global. So PCA does this. PCA reduce if I have 100 number of bands, or generally it's 200 or more than that. I have 200 number of bands. It will reduce it to 20 bands. So what it does is how it reduces it. It's basically take the maximum information in these 20 bands. This is VFix. We tell, okay, take the 20 bands, which is having the maximum number of bands. So in this way, other remaining 180 bands information will be lost, even if they have 0.1% of information.
Yeah, but that's not what I'm saying. I'm saying that you are. So, for example, if your plane is white, or if it's maybe not white, but if it's yellow or blue, maybe if you know that it's blue because of several factors like the different materials that are used for the painting.
Okay.
Maybe it's more relevant to know that it's blue and not that it's just that it's different from light yellow.
Okay. So like the question is like how I distinguish between bands which are very like similar to each other, something like this.
I'm trying to formulate it.
It's okay. Maybe you can, if you're comfortable in French, you can tell and they can interpret me if it is okay. Maybe like.
Yeah, in fact, I have the thing that you only use local information with a CNN, which is the call, and using a CNN for the spectral part feels like you might miss information in the absolute wavelength value instead of the relative one.
Okay, so there's something called contextual information. I don't know if you know that. So in contextual information means the spatial information in X and Y thing. So I take contextual information as well as spectral information, and that is why I do not want to So like people, what they used to do is they do contextual information, they use spectral information, and they used to layer them, like stack them. But that's I don't want to do, because then stacking again will lose some information. So what I did was I used 3D convolution, so I don't have to do them separately. I can do all three of them, like contextual, which means X and Y, and the like the Z, all together. So
I think that what you're mentioning, which is how can you use the relation between the blue and the red, which are very far away bands. I think you can see that with 3D convolutions, because you are at each level you are reducing the dimension, reducing the number of bands, reducing the size of the network, the shape, the size of the cube. But each time you keep the cube, so you keep the information all along the process. But as the bands are summarized thanks to convolutions, closer and closer to each other, and then you can deduce some things like that. I think this is. If the question is how to relate a band which is the 3 or 4, the fourth band with the 200 bands.
Yeah, it was mainly to say that with CNN you will only learn how to deal with how images are related from wavelengths that are close to each other. And you will just do that several times. It was just that I had the feeling that you might have a different way, a better way to treat, to analyze the information if you know the wavelengths. So for example, maybe you won't do the same thing for the wavelengths that are close to red than the ones that are close to blue. And with the CNN, you will do exactly the same thing.
As you have different kernels, you can, just choose a pattern which is proper to specific to blue channels. Look if there are if the same pattern appears somewhere else, and the same for red, etc. Depends on the number of kernels you're using. I don't know. I mean, what you were saying is just the patterns that are extracted in blue are not the same as the pattern which will be visible in red. But with 3D kernels, you will extract the same pattern whether it's blue or red.
all right.
Yeah, but we are dealing with continuous value.
Yeah.
So there is no really blue or red. Every value is a blue or a red. So you will need an infinite number of kernels to deal with all that.
Yeah. The idea of function is then to keep only the relevant ones.
Yeah, I see how we can get information about the wavelengths, but it's still not obvious. And will you have exactly the same sampling of the wavelengths? I mean, will all of those satellites all use the same wavelengths?
That is why we have continuous wavelength. So every band is taken in a different wavelength. So if we have an electromagnetic spectrum, this is where I am taking my band. So if this ranges from 0.4 example 4 to 0.7, so in this 0.4 to 0.7, in every different wavelength there will be a band. So that is why we have continuous, like if one band, two band, like they're very narrow. They're like at every point 0, 1.02, like it's like this. So that is why they're like continuous wavelength thing. Unlike multispectral, where we have, for example, a band at 0.4, a band at 0.5, and a band at 0.6. So that is why we have discrete.
Yeah, but so they all will use a band between 0.1 and 0.7, or will it change from a satellite to another?
Satellite, of course, like if like other sensors, what sensor specification they have. It's similar to like the phone pixels, you know, every phone pixels resolution of.
Okay, so it means that it has to perform.
No.
But if you have information about how do you use what wavelengths you use? If you do that from one satellite or another, it's the same information you find on a specific wavelength. So if you saw satellite, you can use it for another.
Yes, of course. And I showed you like 4 images. All those 4 images are from different satellites. So every image, okay. If I'm talking about multispectral, since all are like optical images, so the range is fixed. So they will be into visible light or near infrared to, you know, so that is fixed. So, but their resolution can vary. Their resolution can vary. Their swat bit, like the area by which a hyperspectral sensor is taking, that can vary. So these stuff vary, and that is why to generalize our model, we do it on different data or different sites to see how the results will be, or it will be just specific to one particular data.
I'm so sorry, as the master of time, I have to stop now. I mean, it's just a bit more than 1 hour that we are here, so I saw a lot of persons just leaving and coming, so maybe might be time to stop here. If you want to continue, you can continue just the meeting. Don't hesitate. Well, thank you everyone for being here once more, and well, I'm going to stop the recording first. And we'll see you next time.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.